Oh, so the camera is, okay, that's what we're seeing.
Maybe you should try it again, because the lighting's different. Andy's in a costume.
It's okay.
Jackson, just give it one more try.
Figure it out. Okay, so you can, let me try putting something in here. I had a roll of toilet paper. Let me just see. Excuse me. Excuse me all the way.
Okay, yeah.
Hi, welcome. Is you here for the show?
Cameraman. Try and live stream.
I can't.
Do it one more time.
I'm not going to do it now.
Why? You're afraid they're going to terminate the channel?
It's fine, it's my step.
What? Is it risky? I'm just saying you should try again.
You said it. That's it. He heard you. It's okay. You can consider yourself heard. Do you think we have everybody? We'll wait. All right. So, let's talk about microwaves. Here's the story that I was told when I was in college, which I don't know if I believe it or not. There was a guy, a science professor, physics professor, and he was working on developing microwaves. Okay, and he every morning his wife would give him a lunch, and he'd take it and put it on a certain spot on the table, and later he'd eat his lunch. Okay. Well, one day he was playing around with the microwave. One day his wife, horrified, realized that instead of giving him hard-boiled eggs, she had given him raw eggs. So he comes home and he says, "Oh, I'm so sorry, honey. I know you must have been so upset with me when you opened up and found out you had raw eggs." He said, "What are you talking about? I didn't have raw eggs. My eggs were cooked." And then he goes back and found out that the microwave that he was working with had cooked the eggs. Now, I don't know if that story is true. It sounds possible to me. But that's the story I heard when I was in college. And that's how they discovered that you could cook with a microwave oven. Now, we have a microwave antenna. I have that, and I was going to play with that at Physics Club later in the year. I used to have one, and I hope this works, but this is what a microwave antenna looks like. Just like this is a microwave receiver, okay? It doesn't require any power. You hit microwaves with it, and you can read a knob here, and you can see how much strength it has. And we can do all kinds of cool experiments with microwaves. So microwave is nothing special. Microwave just happens to be something in what's called the electromagnetic spectrum. I have a picture up here of the entire electromagnetic spectrum. It goes from radio waves on the one extreme to the other extreme is X-rays and gamma rays. And so microwaves is just something in the middle of there. Okay, thank you. But they choose a specific frequency for microwave ovens.
All right.
Anybody have a suggestion how they arrived at what the best frequency would be for microwave ovens? Okay. Yes. Not the size, but it is related to water molecules. I'm going to erase the board. So, it's what do you think it could be about water molecules that they chose to set the perfect frequency for a microwave oven? It's not the size. Okay, so what do we know about, now I'm going to ask you, if you haven't taken chemistry, you still might know this stuff. What's the difference between a polar molecule and a non-polar molecule? Does anybody remember chemistry? Yes, what is that? No, they both have neutral charge.
They have a polar molecule on one side and a slightly more charged.
Right. Okay. So what can you tell me about water? Is it polar or unpolar or non-polar? It's got a plus side and a minus side, right? Water looks like this. It's got an oxygen, which is mostly negative, and it's got two protons, which tend to be around here, which are the hydrogens, and like that. So now, if I hit this with an electric field that's oriented in such a way, I can flip this around. I can rotate this. And so what you do is you choose the frequency that's the perfect frequency to oscillate the water molecule.
Oh, that's me. Sorry.
And then all you do is you cook it from the inside. Microwave ovens don't do anything more than they pick the frequency for oscillating water. And everything else that happens is just cooking the food from the water in the food. That's how a microwave oven works. Now, so what are microwaves? They're invisible. They're electromagnetic radiation. Are you here for the show?
Sorry?
Are you here? Why are you here?
Is this Physics Club?
Yes, you here for the Physics Club show? No, come on in. Okay. So, please sign the attendance sheet. Okay. Yeah. Sit down. Get yourself a nice, comfortable seat. So, now, the frequency happens to be, I forgot, it's in the gigahertz range. What's the frequency of a microwave? I just had it up, I had a PowerPoint of it just the other second. I'll Google it. There it is. 2.45 gigahertz. A giga, 2.45. A hertz means a cycle per second. 1 hertz would be, 1 hertz is like this. One cycle per second. 100 hertz is blah, 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 100 times. What's a giga mean? 10 to the, no, giga is 10 to the 9th. It's a billion. It's a billion hertz. So it's a very low frequency from the point of view of like the light waves and things like that. It's a very low frequency. It's more than radio wave, higher frequency than radio waves. And the wavelength of a is about this big. It's about a centimeter. The wavelength of a microwave is around a centimeter in size. So it's nowhere near the molecule size. So that it's the molecule frequency. It's the right frequency to get the water to oscillate. Okay, so we can put water in the microwave, but if we took liquid nitrogen and put it in the microwave and turned it on, it wouldn't heat up. Liquid nitrogen is not polar. It wouldn't heat up. It's a cool demonstration if you happen to have liquid nitrogen around. Okay, so, but I have some water here, and when I was growing up, there was a commercial on TV. They said, ivory soap is so pure that it floats. It floats. That was their big selling point. You want to wash yourself with ivory soap because it's so pure, it's 99 point, they used to say it's 99 point something % pure, that it floats. But what is the floating telling you about it? What does that tell you about its purity? What? What is it? Why does it float?
Because it has a lower density than water.
Lower density than water. Why does it have lower density than water? Because there's air in there. There's air in there. And that's why it floats. Now, let's put that into, I'm not sure how this is going to work, so you'll have to see.
Yeah. Alex, open.
Let me open it up. Let's put some, okay. I'm not sure how long this will take. Let's give it, that's a lot of soap. Maybe I should cut it in half.
Is there a light inside the...
No, there's not. That's the one thing.
Oh.
Okay, so, but it will, you might have to shine a light into it then, because this is an old microwave.
So,
I can try and use my phone. Will it hurt it? You have a light, don't you? for science, I'll sacrifice my phone.
You're not gonna put this phone in.
No, it's not really working.
All right, forget it. Let's give it. I'll give it 5 minutes. All right, so that's the one thing. The microwave that I got. I wish I had a light. You need a bright light to see. There's nothing going on right now. Can you? Are you seeing a reflection of it, right?
Yeah.
We turn the lights on.
Oh, that's true. That might work.
Oh, there he goes. Okay.
Can we hold it or?
I'll hold it.
Oh wow.
Turn the lights off. You can barely see the soap moving around in there.
You can see it from here though.
Oh, whoa.
What's happening to it?
It's blowing up.
All right, let's.
Getting there.
That's a really good light. Okay. I'm gonna have. This is really gonna be awkward. We're gonna have to do something else. Maybe I can mount it on a post or something. I can give you a rod and something like that. Warm, and you can touch it. It's weird. You can smell it. It smells like it's warm though. Don't be because it's a glass. So you don't want to drop it. It's not that hot. It's a little hot. And it's sort of creamy. It's like making a lotion out of this. So pass it around. Just be careful. Don't be struck that it's warm because I don't want anyone to drop the glass. Let people try it. Feel it. So what happens is the air inside there. There's a lot of moisture in there, and the moisture heated up, and it grew the microwave. Now, it grew the. Let's see. You want to put? Should I make some more? Bigger piece. This is. Yeah. Cool. That's cool. Okay. I'm building up. I want to start slow, so I'm building up things. Maybe. Well, we'll come back to that. So, but a similar principle. Let's try. Have you ever put peeps in the microwave? No.
They tell us not to.
Everyone puts peeps in the microwave. Who brought this in? I want to thank. Okay, here we go. I'll start with 2. I'll just lay them down. So, do you want me to get a stand? I have like another here. Here. It's a broken one, but you can clamp something.
Actually, here, I think
Here, look, I have a. Here.
I don't know what to do with this.
You can clamp it to that.
It has a setting.
Oh, you only have a.
I have a
clamp. What?
I got them to the side.
All right.
Here, let me try.
All right, let's try it with the.
What would happen if we put it on the setting for the baked potato?
Where's the camera in the
I'm just gonna use. It doesn't. It's all this time.
Put the camera in the microwave, then we can see it. Yeah.
Good idea, Serena.
Oh, I see. That's good.
Yeah.
Let's see if that works. Let's try that. But where's your flashlight? I'll use my.
You press that button, hold it.
Okay. Let's try it. Let's turn the lights. Let's give it. I'll give it.
That actually works.
I'll try and do it like this so I don't.
You could
You want me to do it?
twist
Do you want me to hold it so you can demonstrate?
Is there a way to leave it on?
yeah, you twist the top.
Oh,
And you keep twisting it.
figure it out. Come on. Oh, you're missing it.
I got it.
There we go.
There's 2 settings. There's high and low.
Hi.
All right, let's take it out and take a look.
Did they get any
We
bigger?
put it in for
Is it edible?
It wants, yeah, it is edible, but I don't trust.
What are you doing, Robo?
Okay, you want me to hold it even closer and make
Yeah, did you hear that? Your speakers popped.
Yeah, I know. Let's unplug.
the
Turn that off. Okay.
the waves?
No.
Oh, they're deflating now.
Yeah, deflated because the air is cooling down. It's getting back.
Oh wow, that was fast.
Oh, this is really good, Jack. This is great.
I can make it bigger.
Make the peeps bigger.
Wow, perfect.
Oh, this is working great. I have a clamp. I could build a. I could set. This is good. Okay. Now let's take a look. All right. It's just marshmallows. The same thing works with marshmallows. And so one of the things people do, and I don't know if I want to, you take a bunch of these. The peeps. This is not really the peeps. The peeps, you know, the bird ones. They come down on Easter. You put toothpicks on it. You put them across from each other, and you give one a name and you give the other a name. And then they grow, and one of them attacks the other with the toothpick. So you have peep wars.
I mean, do you have any toothpicks?
So we're not going to. This is what happens when it cools down. It gets flat again.
Perfect.
Okay.
Wait, switch the camera view. I want to try a camera. I want to try a light.
Yeah, this is a full recording.
So
This one's going for
so you know why they rotate the where there's they always move. What's going on? You sit down. You know why they always rotate in a microwave? They don't need to do that in an oven. Yes? Yeah, there's hot spots. In fact, we're going to try an experiment in a little while. And what I'd like people to do is we're going to take out the rotation. We're going to take a flat thing. I need to make a flat spread of marshmallow in a flat plane, and then we're going to cook it, and we're going to see how non-uniform it's cooked. So, like, cut this way. I can just break it. Yeah, I don't care because we're not going to eat it.
How tall do you want it to be?
I want it flat. I want it low.
Okay, like covering the whole
You
plate?
here for the show?
Yeah.
You're not sure? Or
Yeah, this is physics.
Yeah, this is the physics club. You take a few and make a whole flat surface. Here, smush it down. That's good. Yeah, and here you can break it. Like.
You want to lower that then?
No, that's good. Just spread it all out. But I want to see how you. There's actually there's a method to my madness, so we'll do that and smush it out. You work on that. Okay. Now, one of the things that most people don't know. You guys, take some tools. Make sure you sign the sign-up sheet. That's important. One of the things that most people don't know, the utility of microwaves is amazing. Like, for example, most people don't realize that if you ever have a CD, you don't use them that much anymore, a DVD, and you want to erase the data on your DVD, most people think, well, you can't do that. So what you do is, it doesn't take long. You just take your, where did I put this? You take your DVD, you give it like a couple seconds in the microwave, and you've got all the data removed. It's pretty cool, pretty cool. And I'm going to show that to you right now. So I just need a pair of scissors, which are right here. So this is a fresh DVD, but I'll show you how it works. But basically, you got to catch this because it's going to happen quick now. You don't need a light for this one. Okay? So here's a regular CD or DVD. This one's a DVD, I believe. Let's see. Could be a Blu-ray, would be the same thing. This is a CD. Okay? And I can, another time if you want, I can give you a whole day on how a CD works. But it's pretty cool. So I'll take this rotating platform out because I want it to be that you keep it, that you can see it. And put this out of the way. So here's the CD. and I'm going to erase the data that's on that CD. It'll only take a few seconds.
That's your best job.
All erased.
It's also fractured.
Yeah, it's all erased. It just doesn't work anymore.
Let me make another one. I'll make another one.
Is that a certain pattern?
Yeah,
It's,
there's a name, it's like Lichtenfrost or something. What's the name for those like pattern?
I don't know. Yeah. Let's make another one. Lights, please. You have a big job now.
That was straight up fire.
Now, what you don't know about CDs are, so obviously this erased all the data. I didn't say you could use it again, but obviously it worked. It erased all the data.
Well, if you just want to erase it and not use it again, just like break the CD. Why microwave it?
I'm kidding. Anyway, so a CD, what's inside a CD is a micrometer wide spiral, and it ravels around. And on that spiral, there's little tiny bumps, very sharp edges though. If you think about it, very very sharp edges. Sharp edges attract electric fields. They electric charge accumulates on sharp edges. And now what you've got is a micrometer wide thing, and it wraps around. And if you unraveled it, it's about 3 kilometers long. What's on the floor? Really, think about what's inside of this thing. It's a micrometer long. It's really heavy. And if you stretch it out, it's like 10 kilometers long. Unravel this whole thing. That's what's on a CD. The difference between a CD and a DVD and a Blu-ray, they're all basically the same idea, but what changes is it gets skinnier and longer, so that because the technology improves, so you got skinnier and skinnier, longer and longer, so you put more and more stuff on it. And all you do is you take this thing and you put little bumps on it, and the bumps become data. It either becomes reflecting or non-reflecting. That's how you. Now this technology is almost gone already because now everything is done on the internet. Oh, that looks great. That looks really good.
Thank you.
So let's put a mark on here. I really want to make sure this doesn't turn. Oh, it's going to turn. So I need a little
Maybe use like tiny like wooden
cup.
like cubes or something.
This cup will do it. Yeah, there we go. Let's give it. Let's see if this works. It's not. I don't. But I want to see what the pattern. You can leave that on. Lights on now. Please let the lights on. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, we have to give it more power. Power level.
Dr. Malcolm, what would happen if you microwaved a record?
You would destroy it.
So, like, would it have the same effect, or?
I think I don't know. It's plastic, so this has metal in it. So it's metal attracts the electric field. I don't see a pattern. It's not my microwave. It came from was found on the street.
It may or may not blow up.
What you might not know, you guys know Mr. Polito, another science teacher here in the building? I've gotten to meet him this year. I know I'm new here, and I really didn't get to meet him last year. He's a great guy. He finds things. He's great at finding things. He finds a lot of the stuff that you've been touching in my classes. He found them in New York. Oh no, it didn't work. All right.
I'm sorry, my artwork was not.
No, it's smushed up. All right, I forgot about that. So, you gotta work. Another way to do this is with toast and butter. You take dry toast and you smear it with butter, You gotta make the toast first, and then smear it with butter. You take the rotating thing out of the microwave, and then you'll see a pattern of grid lines. If you take the grid lines and you measure the spacing, and you know the frequency, you can actually determine the speed of light. And it comes out right. You just take the spacing, that gives you half the wavelength of and you know the frequency, and from that you take the product of those two. The wavelength times the frequency is the speed. Some of you might have heard about that in your geoscience classes, right? Or not, I guess. All right, I wonder what would happen if I microwave a light bulb. What would happen if I microwave a light bulb?
Will it turn on? That'd be cool.
I think I'll put this back in there. Sorry, for the real world. I want it to work. Lights. Okay, let's start with a regular. This is a broken light bulb I made for later. Let's start with a regular light bulb. Let's just turn it on and cook the light bulb. This is something you should definitely not do at home. Lights off. It's lighting up. Look.
Did it burn out?
I don't think, might have, I don't know. Lights on, please.
Do we really want to plug it in?
So a light bulb is nothing more, all that a light bulb is a wire, and this is the light bulb. And there's the round part of the light bulb that's like the screwed part, and in the middle there's a spacer, which is insulating current doesn't flow, and then in the middle there's another spot. My son's the kids in my EM class have just tested this. You put current in this side, you take the current out that side, and it goes through the wire. The wire heats up because the current flows through it. It's the kind of wire that heats up when current flows through it, because it's resistive to the current, which means basically it heats up, and it gets hot and glows. So I don't need to run current through this thing to glow. I can take the electrons in the wire, which are free to move, and use the microwaves to shake them up. Instead of molecules, I can use the microwaves, and I can use the microwaves in a light bulb and shake it up. So I took a light bulb before. Oops. What happened? Did it break? Oh no, that's you're alive.
Sorry, I don't want to
Oh,
pull it out by the cord.
is that all right? Okay.
Indestructible.
I took a light bulb and I put it in one of these masks. They're very convenient for this purpose. And I smashed it with a hammer. And I took away all the glass. So I don't know what's going to happen, but I think it should light up. Yeah, it works. So even a broken light bulb lights up in a microwave.
Dr. Kaplan?
Yeah.
Why is the pattern on the CD the same on both sides? Is it because the CDs? Because usually
You're seeing
CDs
through it. You're just seeing
Oh, I'm
through
seeing
it.
through it. So it's only
One
on
side
the
of one side of the CD is clear.
It's clear, right? That's what.
Light goes in and out the bottom, and the top is where all the information is stored.
Okay, so
That's for another day. I'll give you a whole CD story. Okay. This is my cell phone. Let me not get it anywhere near the microwave. All right. You see what it does.
Yeah, I don't want to see like this.
All right. So let's see what I got here. So
What happens if you microwave that same light bulb again?
it'll light up again. Here's another kind of light bulb, clear light bulb. You can try that. And I have a fluorescent bulb here. I think it's in my.
Fluorescent will be fun.
It's in my briefcase. Now, a fluorescent bulb is different. A fluorescent bulb doesn't have any wires inside. It's just gas.
So an LED probably wouldn't work, right?
Oh, I do have an LED, and it did work.
It did work. Wow.
Yeah, and I didn't expect it to work, but I brought it with me today. but it wasn't very bright. I'll show you the LED. I actually had the fluorescent bulb. Maybe it's, give me a second, I apologize, I'm checking my back room.
No one's ever said that. No, they've never. Who says that? Who are you running? Who are you running? What are you Graham?
Never to look at the microwave?
Why? It can give you cancer.
If you look at it. But if you don't look at it, the waves just don't come in.
No, actually no, it's not, microwave radiation is non-ionizing, it'll only burn you, it won't give you cancer.
That's some way to disprove that. Or maybe not, maybe they can, I don't know. To be fair.
Oh, here we go. So, I found one of these.
You're gonna leave it in the packaging, or are you gonna?
No, I'm gonna take it out of the package.
I don't know, I think I know.
That's microwave plastic.
Now, there's no wires in a fluorescent bulb. It's filled with gas. The gas can get excited by the microwaves, though. Oh, this works. This is pretty big.
As long as it doesn't explode.
Well, actually, it could explode too. Oh my god.
Right, wow.
Can you see it? Can you get the angle down a little bit lower? Oh, I'm screwing it up. Can this is. Can you want to help me with this? Yeah. It's a little loose here now. I didn't want to break it.
Oh god. Technical difficult piece.
Oh, it smells awful.
Yeah, it smells really bad. All right, so let's get this.
What does it smell like?
It smells like a microwave fluorescent bulb.
Yeah, that's what it smells like.
Maybe put something to
Like
stop
ozone.
the door
Right,
from
we're gonna-
swinging so far.
What?
Jackson, maybe stop something from, put something to stop the door from swinging.
No, that's too much work right now.
No, like, you just put like that.
I should put a second tripod, that's my mistake.
Just put a second pot or something, like that ceramic pot over there.
You should like clickbait the title. Like praise physics teacher microwave
Probably, you
school
remember the trick of
ending
getting it
surprise.
stuck up embedded?
Yeah,
Probably use
something
mini
like that.
marshmallows. That might
Giveaway at the end.
Yeah.
This didn't blow up that much either.
I'm sorry, I probably stuffed them too close to each other.
Let's put one marshmallow in by itself and just let it run for a second.
Alright, thank you, have a good weekend.
Me too, hold on. You're missing the big surprise ending, but that's okay. It's up to you. Well, now I need a light.
Here, go on.
No.
It's one marshmallow.
That's one marshmallow.
Hey, yo.
If you want, I can stand a little closer and help you with this.
Oh my god.
Oh!
Oh, wow.
Careful, it's already small.
Huh. Okay.
Here, Toby, you want to switch places?
Yeah.
So when my kids were growing up, I used to read them a story called The Frankenbagel Monster. It was one of my favorite stories to read to them. It was about this bagel maker who, when nobody was looking in the evenings, would make monster bagels in his basement. And then this one monster bagel, the Frankenbagel monster, grew larger and larger and was going to attack. It was about to attack a cream cheese factory. And they knew that once the Frankenbagel monster would get to the cream cheese factory, it would get all the, the bagels get lots of power from cream cheese. It would get all that cream cheese power, and then it would be unstoppable. So there was this guy who was the inspector, and he said, "Oh, I know how to stop the bagel." He says, "What should I do?" He says, "What do you do?" He says, "Just whatever I say, go along with me." He says, "Okay." So they're two standing there. This is reminding me of the Frankenbagel monster. That's why I'm remembering this. They say, "All right, what should we do?" He says, "That's a nice looking bagel. I think we should eat that bagel." He goes, "Come on." "Oh yeah, let's eat the bagel." "Yeah, let's eat it right now. Let's eat the bagel." And the bagel stops moving, and then it comes to a complete stop. They said, "How did you know that would work?" He said, "It's a known fact that all bagels get stale right before you're about to eat them." That was the punchline of the whole book. All right, this is the part I like the most. What I want to do. Where's my matches? I want to put a candle in the microwave. You really got to catch this. It's going to be dark. We're going to just the light from the candle will be enough.
Yeah, that should be enough.
Are you going to be able to? Is the angle going to be right when I put? Okay. Now what I did is I burnt a lot of matches, and I put the carbon from the matches inside there. Can't blow with the mask on. You can't blow out a candle.
Well, the mask, that means the mask's doing its job.
Okay.
It's not going to. Hopefully.
Yeah, he lit the match, or the candle.
Let's give it a little longer. Did you see that?
Oh, it smells like bacon.
No, it just smells like matches.
It's only bacon.
Well, I didn't hear what you said.
What are the chances of explosives in the middle?
Oh, very unlikely.
Never zero.
Why is it like blowing in the breeze almost? Oh yeah.
I don't see it. Light going out. Let's see if it still does. You went like that for a second. Maybe that was the end of the microwave. I don't know.
Really?
I've done this demonstration many times, but
Never had a burnt out microwave.
I never had a microwave that was found on the streets. Let's
Is
see if
that
the microwave's
possible,
still-
Ethan? Like the magnetron just breaking?
Yeah.
Yeah, it's an old one.
Put the light in there, please, so I can see if it's growing. Oh, the microwave's not broken. Look.
A round of applause for the microwave that won't break.
Okay. What I was hoping for, the big surprise ending is usually with the candle. I'm going to try and give it another try. Well, let me turn the lights on for a second. So how many people here have never been to Physics Club before? Raise your hand. Okay. So let me tell you a little bit about Physics Club, just as a advertisement. We meet every Friday, and we compete for the first half of the year up until the middle of January. We compete in the Physics Olympics, which means we're preparing for that, which is a bunch of the different events that we have to prepare for. We have to build things. It's not that different from some of the other clubs in that sense, but we build things. And last year we came in first place, and I actually polished it up. We came in first place in the state, and we got the coveted. We got to keep. I don't want to get marshmallow on it. The coveted Physics Olympics bowl, and it has on it 30 years of high school names of teams that have won, and ours is the last team. And now we have, since they won't fit anymore, they have to put another block beneath it to make it bigger. This has been, and each time that you win, you get to keep it in your school for 1 year. I'm arranging to put it in the little display case right next to my classroom over there. I have the thing, and I got to put it. You get this, and it looks shiny. You get to keep that one. This is the real thing. This is the real coveted thing. If you get to hold on to that, you can see some teams won like 4 years in a row. You can see the history. Now, this is our first year competing, was last year, and now the question is, how long do we get to hold on to it? And so we want to be the team to beat. Montclair, in the history gone by, was known to be one of the top physics schools in the state. I've learned that from my colleagues. It's not there now. We're not there right now. We're not known to be one of the top physics schools in the state. We don't have the equipment for it, and now they have me. We didn't have the, but we have to really have, there's more people now. My goal is to turn this school into, hopefully, the top physics school in the state. It should be. Montclair has the resources in principle to compete with some of the big schools like Chatham, some of the other schools around that are really, and from what I've seen, you got great students in this school. I'm very impressed being your teacher, how great the kids are in this school. Very, very impressive. So Montclair has the raw materials to be unbelievable. Now, it's going to take a while. But if we can hold on, along the way, we can hold on to the physics, if we can hold on to the physics cup. We have to be very clever and work hard. This one is the shiny one. This is not the big deal. This is the big deal to be on that list.
But the shiny one looks nicer.
The shiny one looks nicer, I know, but it's
Made out of a cheaper
from the
material.
point of view, it's like you can say every team gets something, but somebody gets to hold on to the Stanley Cup, for example, that year, or each of the cups. That's the really thing you get to hold on. You got to give it back at the end of the year, unless you win it again. So if you're interested in what we're going to do for the first half of the year, is we will we'll be mostly working on Physics Olympics, preparing for Physics Olympics. And then after the Physics Olympics is done in the middle of January, we'll pick a few different topics. I think one thing that would be fun is to, for example, something I could teach you about how optics works.
That's fine.
That's not.
And we can build, our own
Let's be covered.
optical system, things like that, or maybe not, but I'm going to talk to the physics club and lay out a bunch of examples. That's what we do. All right, so, and then interspersed once in a while, I'd like to have these demonstrations. So I think I've covered, I'm going to try the candle again. You saw how it bzzz, like that? When it works right, you got to go bzzz, bzzz, a lot. So maybe what you're supposed to do to make it work is to burn a lot. What it's doing is it's creating a plasma. You know what a plasma is? What's a plasma? Anyone can offer what a plasma is?
Sorry, I have to go.
Okay.
Bye.
See you next week. So a plasma is like a gas, except it's a gas of charged particles. So it's a form of matter that you don't normally learn about. You learn about solid, liquid, and gas. A plasma, I'm trying to get it to burn out more matters here. That's what helps make this thing work. A plasma is a gas of charged particles. And so the way you make a plasma is you start with, I gotta blow this out. You start with a gas, and then you find a way to get it excited with energy, and that's what the microwaves do. They create a plasma. So of the four of these things, solid, liquid, gas, and plasma, which do you think is the most prevalent type of state of matter in the solar system? Which do you think it is? Why? Why is the plasma the most common way to find matter? Yes?
Stars.
Yeah, the sun is a plasma. The sun is a charged gas. And what that does is the charged particles inside the gas, it's a big gaseous thing, really, is a sun. All stars are. And they get into this excited state. Now, have you heard of the idea of plasma physics? Plasma physics is the idea of building a giant equivalent to a sun in a container. The container is the size of a 10-story building. The idea is that you can build a plasma and use that to excite protons and neutrons to collide with each other. and basically, on Earth, build the same thing that's causing the nuclear collisions that are occurring inside the sun. The sun powers the entire solar system, basically. All this, if you think about it, the source of the energy in the solar system is really the sunlight from the sun. Everything is based on that. And if people could build, and people are working on this, it's in Europe, it's a consortium of a lot of countries. There's also a Chinese version of it that's being worked on. If you could build a plasma source of energy, you could build something called fusion. Have you ever heard of the difference between fission and fusion in your science classes? Okay. Fusion basically takes, with a fusion reactor, you could take seawater, if you can get it working, desalinate it, and just pour the water in and out pops unlimited amounts of energy. So in other words, if we get to the point where we have fusion reactors, there's no longer any country that says, well, I got the oil and I have the source of energy. Basically, and then you could make unlimited amounts of energy. With unlimited amounts of energy, there's so many things that could open up for the world. You have the ability to solve any problem you want to. In principle, you could use that energy to find ways. It's also clean. It's also clean. It doesn't pollute. It doesn't create global warming. It's the silver bullet to the solution of the future. It's your solution because it's going to happen. I probably won't live to see it. I'm 66. It'll probably be another 20 years. Maybe I'll live to see it, 86. But it's your future. You need to know about it because at some point, if that really opens up, that's going to be the real game changer. That's going to be the real game changer. What I'm trying to do is build a small little plasma right above the candle using the heat from the burning to help produce it, and then using the microwaves to ignite the plasma and get it excited. And then produce a little plasma. This wouldn't be the kind of plasma that we use to build nuclear energy, but build a little plasma that we can then see it glow. And then what happens is you see it go things like, if it works, it goes bazoop, bazoop, bazoop. We got one good bazoop out of it, and then it shut down. So I'm going to give it another try. I didn't burn out the microwave yet, so. If I do, I can just ask Mr. Ippolito to please go for another walk in New York City.
I have a microwave I can donate.
That would be very appreciated.
It's very big.
Right now, I've got marshmallows everywhere. I can always wash the marshmallows off. Does anybody have any questions about how any of this stuff, is anything I've done so far? No? Okay.
I have a question.
Yes?
You showed that it would wipe a CD. Out of curiosity, would a microwave also wipe an SSD or a flash drive? I know we don't have any on hand.
It would be, you would put anything there, a flash drive, it's a different principle, but anything you put in the microwave, it's going to be destroyed.
An SSD will like die if you put a magnet near it, so if you put it in
Okay, don't turn the lights off yet, I gotta figure this out.
completely be gone. Plus all the metal inside one.
So, you really don't want to do any of these things like light bulbs in a microwave. You might actually heat it up enough to get some of the metal, which is solder, into your microwave, which would then make lead and tin coated around the inside. Not a great idea. So don't do this at home. There it goes. You see it? We got a little plasma there.
A little burnt.
Was I supposed to be looking at it without like vision protection?
It doesn't matter.
That's awesome.
Okay, folks, well, that's what I planned. I hope you enjoyed it. And,
Thank you, Dr. Kaplan.
now, have a happy Halloween. I like to do it on Halloween because it's sort of spooky stuff, you know.
Dr. Kaplan, can I keep one of the CDs, please?
What?
Can I keep one of the CDs?
Can I keep the other?
You want to keep one?
Yeah.
May I keep the other?
All right.
First comes to first serve.
So now it's